Stephanie, as chair, do you start things?
Yes, I do. And I guess I am chair. Are you ready to start?
I am ready to start.
And we have people on.
And we
too.
have Meyer and Hilla on Zoom,
Okay,
and
they,
you and Andrew, so the committee's here and Benjamin's here. Can folks hear Stephanie?
Barely,
Yes.
but yes.
yeah, come up here and get us started. And the one thing I want to make sure is to make sure that Hilla knows the process of what we're going to do today. So Harry is going to give his presentation. Then we will have questions from the committee. We'll start with the folks who are online for their questions first, and then we'll go to me and Andrew here in the room. And then if we have some time, we'll open it up for general questions for the audience. And then after that, we'll have a closed session. Okay, so go ahead.
Cool. Well, thank you so much, everyone, for coming. Today, I will be defending my dissertation titled Property-Based Testing for the People. And if I can get the clicker to work, maybe not. Come on. One sec. That's that. Here we go. The dissertation is advised by Benjamin Pierce, and my committee is Stephanie Wyrick, Andrew Head, Meyer Naik, and Hilla Peleg, who is at the Technion. So code is ubiquitous. You have software running on your phone. You might even have software running on your refrigerator. And where there is code, there are bugs. It's a natural part of the process. Programmers make mistakes, and the code that they write doesn't do what they intended, or maybe they didn't understand what they were trying to do in the first place. And bugs are a big deal. The 2002 study showed that software vulnerabilities and bugs cause up to $60 billion a year in damage, and that was 20 years ago. In 2022, that number was estimated at $2 trillion per year. And so, if you sort of read the news, you will probably see headlines of software vulnerabilities causing all kinds of problems, including human loss. So, bugs are a big deal. And so in our area of computer science, we think a lot about how to help programmers write code with fewer bugs and how to catch those bugs that they do write before they go out into the world and cause harm. And a flagship way that they do that is testing. Testing is a great way that is a great technique that programmers use to validate that the code does what they're expecting while they're writing it. And specifically today, I'm going to talk to you about property-based testing, which is a specific kind of testing, which I will explain now. So suppose you have some unit of functionality in a program, and you'd like to know that it's correct. A fairly standard approach to testing that is something called example-based unit testing, where a programmer writes down a bunch of cases that they can think of the software behaving in various ways. And they write kind of input-output examples. So they say, when I give the program this, it should do this. This is all well and good, but it takes a lot of time, right? The programmer has to write down each of these examples by hand. And also, it's error-prone. If the programmer misses important key examples, they may not test important use cases. So in property-based testing, we write, instead of input-output examples, a kind of full specification of what the software is supposed to do, a logical representation of that software's specification. And then, so here's an example of such a specification. This specification checks that some invariant for software is maintained. So if a particular data structure is correct at the beginning of the program and we make some changes to it, it remains correct after those changes. And this kind of property would kind of check that, in this case, a binary search tree is implemented in a way that obeys its specification. Once you have a specification, you have to test. And this process looks a little something like this. You have a random data generator, which is producing lots of random inputs to the program. And then and then you check for each of those inputs, does the property that you wrote hold? If you get a bunch of successes, great, you're done. You can have confidence that the property is true. But if you get a counterexample, a failure, it means there's probably something wrong with your code. And then you have a piece of code called a shrinker, which takes that counterexample and tries to make it as small as possible so that you can really isolate the particular problem in the code. My thesis is a bit broader than just property-based testing. I think that combining techniques from programming languages and human-computer interaction areas of computer science leads to significant actionable insights for the development of better software engineering tools. I'm going to argue this thesis in the context of property-based testing and show you how work that I've done in both human-computer interaction and programming languages has impacted the field of property-based testing and software engineering success. In this talk today, I'll talk about 4 papers, which correspond to 4 chapters of my dissertation. The first, property-based testing in practice, is a very human-computer interaction focused piece of work. This is a user study talking with users of property-based testing to understand how they use it and what challenges they face when using it. Then in the second part, I'll give a sort of more programming languages perspective and focus in on some languages that we use for writing random data generators. And then finally, I'll kind of mix and match things in a paper called Lucid Property-Based Testing, where we talk about how developers can better evaluate their testing to see that it was successful. So let's jump right in and talk about property-based testing in practice. This paper was published at ICSE 2024 as a distinguished paper. And in this paper, we asked 2 big research questions. First, what does a successful and mature culture of property-based testing look like? And second, what are some opportunities for future work that we can do motivated by the needs of real property-based testing users? The study had 30 participants from a company called Jane Street. This is a financial technology company that uses property-based testing extensively. And so we hope that by looking at how they use it, we could learn things about how other software companies might be able to successfully use PBT. We split our results into 2 basic categories: observations, which highlight surprising things about how PBT is used, and research opportunities, which point out ideas for new projects that we might be able to embark on. So let me talk about a couple of observations we made. First, property-based testing is useful. Yay. Especially in certain high leverage scenarios, and it helps to build confidence in core components of a software system. There's a bunch of reasons property-based testing is useful, but I'll highlight one that a participant mentioned, which is that the random aspect of property-based testing means that it can help find bugs that you wouldn't have thought of as the programmer. It's sort of exercising situations that you didn't have in mind when you were writing your tests. This is kind of obviously a thing that property-based testing is supposed to be good at, but it was nice to see that developers were actually seeing that benefit in practice. When I say high leverage scenarios, this means that property-based testing wasn't being applied all the time ever. Instead, developers found particular situations in their code where property-based testing was specifically effective. And I mentioned 2 here, differential or model-based testing and round-trip properties. I'm not going to get into the details of those right now, but there's lots more in the dissertation. And property-based testing helps these developers to build confidence in the core components of their software systems. A great quote from one developer in the study is that PBT is useful when you have a really good abstraction with a complicated implementation. And this happens quite often at the core of an application, where you have some piece of code that lots of things rely on, and it provides a pretty consistent API to those pieces of the system. But it itself is quite complicated on the inside. And so you really want to make sure it's correct if the rest of the system is going to be built around it. So much for observation 1. Observation 2 is that property-based testing is used primarily as unit testing. And it's run often during development, and it has to do its job very quickly. I'm highlighting unit testing in opposition to integration testing. Integration testing is where you test the whole software system at once, whereas unit testing is usually done during development, testing individual components in isolation. And we have tools like fuzzers, CAFL, for integration testing randomly. But if you want to do unit testing randomly, property-based testing is really the way to go. And we found that developers were indeed using PBT that way. But because property-based testing is used during development, they were running it really often, sometimes after each edit to their code. And that means property-based testing doesn't have a lot of time to do its job. It's going to run in, just a few seconds, and it needs to find whatever bugs it can find in that amount of time. This is a change to the way that we sometimes think of property-based testing tools being used. The current literature doesn't emphasize performance in the way I think it needs to. Okay, so let's talk about some opportunities for research in this area. The first is to improve automation, especially for generators and shrinkers that need to satisfy complex preconditions. Automation is kind of always important in software engineering, but it's especially important in this case because it's happening at a time when developers don't feel like they want to be distracted by yet another task. They think testing is my goal, I want to focus on testing, and they don't see writing generators and shrinkers as kind of on their critical path. And so automation here is really important to keep them moving. And this automation is difficult because the data that we're generating and shrinking needs to satisfy some pretty complex preconditions. Developers in the study were generating things like valid XML documents, well-typed programs, compliant financial exchange messages, and all of these need pretty complex logic to generate correctly and shrink correctly. And so this is a real challenge, I think, for property-based testing tool developers, is to build automation that can contend with complex preconditions like this. And then opportunity 2 is that developers don't always check their testing success, and so we need to help build tools for testing evaluation. Over a third of participants in the study admitted that they don't think as hard as they should about testing effectiveness, which means they sometimes may be in a situation where they've done a bunch of work to do property-based testing, but then at the end didn't quite check that it was as effective as they wanted. This is a real shame, and we think that some better developer tooling is a good answer. And so we can help build tools that give developers better insights into what was happening during their testing so that they can have a good sense of whether it succeeded or failed. There are more observations and research opportunities in the dissertation. But the upshot of this section is that talking to real-world PBT users gives us insight into how to design better testing tools. And in particular, developers need better access to fast generators and shrinkers that they can use to test their properties, and better tools for evaluating testing effectiveness. And these insights are going to inform the work in the rest of the dissertation, where I embark on improvements to generators, shrinkers, and tools for evaluating effectiveness. Do I have any questions up to this point? Also, can I do a quick time check? Because I realized I didn't check when we started.
We started at
9:35. Okay, got it. Um,
How long do you anticipate until?
35, I should probably go until, let's call it, let's call it 10:20. Yeah, that seems about right. Okay, so now let's talk about parsing randomness and reflecting on randomness. These are two papers that to give better tools for generation and shrinking. And a little outline of this section is that I'll give you some background on sort of the current state of the art for data generation. And then I'll talk about these two papers and the contributions they make. So what's hard about random data generation? This is the same property that I showed you before, although in a different language, forgive me. The property is still checking that when you modify a data structure, that the data structure's validity is kind of maintained through that modification. And if you look carefully at this property, you'll see a kind of implication, right? We say if T is a valid binary search tree, then a bunch of other stuff. But it's hard in general to generate values for T that satisfy this precondition. And if you're not careful, you'll do a bunch of work generating things that end up getting thrown away. And you'll waste a bunch of time not testing things. But what's worse is that even if you are generating valid things, these are all valid binary search trees. They're uninteresting. There's repeats, duplicates. They're too small to actually trigger interesting behaviors in the program. And so when we think about generation, there's really two goals. One is that the inputs that we generate are valid with respect to the precondition of the property. And two is that the values are interesting enough to trigger a broad range of behaviors and bugs in the program. Now, interesting is not super well defined here, but let's punt on that for now. But keep those in mind, valid and interesting, as kind of really important in this process. So now I'm going to talk about the kind of state of the art in this space, which is monadic generators. And this is a kind of language for writing down data generators. And this is a generator for trees, so generator for kind of binary trees of data. And I will kind of read what this means to you. So the generator is going to make a random choice and do one of two things. Either it's going to just return a leaf, an empty tree with nothing in it, or it's going to pick a value between 1 and 10, then recursively generate a tree for the left and a tree for the right, and then it's going to package that back up into a node. And so this generator does generate a whole range of trees. But if you try to use this to test the property I showed you just a moment ago, it does not enforce this binary search tree precondition, this well-formedness condition. If you want that, you have to do a little bit more work. So this generator actually does do the thing you want. It takes two integers as input. Now we've got a kind of input going on. If low is greater than high, if the range that we're trying to generate in is empty, then we have to return a leaf. We have no choice. Otherwise, we may still return a leaf. Or now we're going to generate not between 1 and 10, but within a specific range of values. And when we recurse to the left and the right, we're going to make sure that everything on the left is less than X and everything on the right is greater. And in this way, we're going to maintain an ordering in the tree, which is the invariant for these binary search trees. And of course, then you sort of package this all back up into a node. If you want to get fancier and get at the kind of interestingness aspect, you can also do things like this, where you modify the frequency with which different choices are made so that you can bias the generator towards larger trees, which are more likely to trigger bugs. So that's the background on monadic generators. And now I'm going to talk to you about some modifications that we've made to this paradigm. So the first paper, Parsing Randomness, which was presented at UPSLA 2022, The idea is that we make these generators easier to tune, easier to kind of make the distribution interesting by viewing them as parsers. We introduce free generators and provide new algorithms for generation based on this idea. In order to explain free generators, we need to talk for a second about choices. In the generator I showed you before, there are two places where random choices get made. One is the one of, and the other is the choose. And we can actually look at what choices are made when generating a particular value to understand what's going on here. So in order to generate this little tree, the first thing we have to do is choose a node, because if we chose a leaf, we'd make an empty tree. Then we choose the value 3 for that node. Then we choose leaf for the left-hand side, node for the right-hand side, the value 5, leaf, and leaf. And these are the choices. This sequence of choices produces this tree. But if you kind of squint at it, you can instead think of this process as parsing a list of choices into a structured value. And this perspective on generation is going to be really useful. So now I'll talk about free generators. What we're going to do is we're going to do both the kind of standard random generation and this parsing form of generation in the same program. And we're going to do it by writing an uninterpreted program, a program that kind of is inert, and then we're going to interpret it in two different ways. This uses a concept called Fourier monads, which I don't have time to get into. And the generator itself, this is the old generator, and this is the change we're going to make to it. Almost nothing. In fact, the little changes here with the leaf and the node are kind of superfluous. We don't really need it. It's easier to explain this way. Now, the main thing I've changed is the type, although I'm lying a little bit, because by changing the type, I've also changed the interpretation of a whole bunch of these basic operations. But I think what's going on under the hood isn't as important as what this really does, which is nothing. When you run this program, you get a data structure, not some random program. And it kind of looks like this. You can think of this program as defining a flowchart, where the nodes, the nodes of the flowchart are the choice points in the program, and the edges are the different choices that can be made at those choice points. And so now this flowchart can be used for random generation by kind of randomly picking edges and following them. Or it can be used for parsing by looking at some list of choices that you have, picking one and saying, okay, I can use this to make a choice. And so what we can do is we define interpretations, which I'll show with these square brackets, which interpret the flowchart in each of the various ways that we can interpret it. There's three interpretations that we define in the paper: the generator interpretation, which turns it into a standard generator, the parser interpretation, which turns it into a parser, and then the randomness interpretation, which basically says, just give me the choices. Just randomly make choices, but then don't do anything with them. And it turns out that if you generate something with the randomness interpretation, you generate some choices with the randomness interpretation, and then you parse those choices, that sort of composition is the same as just calling the generator interpretation in the first place. And this is where we get the kind of tagline for this paper, which is that a generator is a parser of randomness. So what can we do with this? Well, I'm going to talk about an algorithm called choice gradient sampling, which leverages the way that we've set things up here. There's really two things that we've gained from making this switch. The first is that we can manipulate choices as first-class objects. We can make some choices, mess with them, and then use those choices to produce values. But I'm going to talk about that in a second. What I'm going to talk about now is that we can actually manipulate the generators themselves. So the derivative of a parser with respect to some character is a new parser that assumes that that character was already parsed. This is a standard thing in the parsing literature, these derivatives. And we're going to do the same trick with generators. So the derivative of a generator with respect to a choice is a new generator that assumes that choice has already been made. You sort of bake in the first choice and then continue on generating. I'll give you an example of what this looks like. So this is the body of the generator I showed you before, and we're going to take its derivative with respect to the choice node. Take a second to see what you think this might look like. Okay, we're going to skip past the first outer one of, and just fix the choice where we've already chosen that we're going to be generating a node. The resulting generator always generates a node, but then continues on like a normal generator. We can do it again, this time taking the derivative with respect to the choice 5. And what we find is that we skip down past the choose and bake the value 5 in everywhere we saw x. Okay, so why am I telling you all of this? Well, these derivatives that we can take enable interesting new algorithms for manipulating generators. And one is called choice gradient sampling. The idea is we use a process of kind of repeated derivatives to guide the generator towards interesting things. And interesting things in this case are valid values, values that are valid with respect to a particular precondition. And this algorithm can turn a really naive generator, like the first one I showed you, into one that more frequently satisfies the preconditions of the properties and is therefore more useful for testing. There's more details on this algorithm in the dissertation, but the results are that when we tried to generate values with choice gradient sampling, we found that in general, they generated larger and more interesting values, and a wider variety of values. And so we think that this is kind of good evidence that choice gradient sampling kind of moves the needle in terms of being a better place to start than just a kind of standard generator off the shelf. Okay, next I'll talk about reflecting on random generation, which builds on free generators to instead help with shrinking. Reflecting on random generation was published at ICFP 2023 as a distinguished paper, and it extends free generators with the ability to run in reverse. This is a little bit weird, but the idea is that whereas a generator goes from choices to values, a reflective generator can go backward from values to the choices that would have produced those values. And this is useful for shrinking, generator tuning, and other things. Let's talk about why I'm talking about shrinking in the context of generators. So I'll set up with an example. Suppose I've got a program that takes a big data file and analyzes it. If a user comes to me and says, hey, my data file causes your code to crash. Can you fix your code so that it doesn't crash on my data file? The problem might be that their data file is quite large. And so it's really difficult to know which part of their data file is causing a problem for your code. What you'd like is some kind of process by which you can turn their data file into a simpler one. And that simpler one is still causes your code to fail, but now it's kind of obvious which part of it causes your code to fail. And we don't want to do this by hand. We instead want this process to be automatic. Here's an idea that we could use based on what we've learned about free generators. We could, because generators are parsers of choices, take the choices that produce this data file, then we shrink the choices, and then we regenerate by parsing those choices. Rather than trying to shrink the data file directly, we instead shrink the randomness or shrink the choices. This would be a great way to do things, except we don't have the choices. All we have is the data file. What we'd like is a way to go backward to get the choices so that we can make this whole process work. By the way, this process of using the generator for shrinking in this way, without this backward arrow, is standard in the literature. And so, okay, what can we do with this? Well, what if we ran the generator backward? What if we took a generator for those data files, ran it backward to get choices, and then shrunk the choices and then regenerated? And that is exactly what reflective generators can do. They extend free generators with extra operations based on partial monadic profunctors, which I definitely won't get into today. And it allows users to annotate their generators with instructions on kind of how to undo each step so that the whole program can run both forward and backward. Let me show you what it looks like. I'm not going to get into what these annotations mean, but just see that it's not significantly more complicated than the original generator. And when I say run backward, I'm lying a little bit. What's actually happening is that the program is running forward with an input that it's kind of looking at as it goes and saying, okay, how would I make this choice? How would I make that choice? So it kind of looks at the first part and says, okay, what choices would I need to make to generate that first part? And then looks at the second part, what choices would I need to generate that part, on, until at the end, it has generated a full, it has produced a full set of choices that would, when made in the forward direction, produce the value. And then all of this kind of just works. You can use a generator backward to get choices from a value, shrink the choices, and then get a shrunken value without having to write a shrinker by hand for the values themselves. There's a lot more with reflective generators that I didn't have time to get into in this talk. They can do other things with generation, not just shrinking. And there's a bunch of other cool kind of use cases. There's also proofs, experimental results, examples. We did a lot in that paper. The upshot of this whole section is that free and reflective generators and abstractions like them can give the developer better access to high quality generators and shrinkers, so that programmers have an easier time getting started with property-based testing, and have more utility while doing it. Any questions up to this point about any of this stuff? Okay, keep going. No. Okay. So the final piece of the dissertation is now focused instead on testing effectiveness. Now that we've gone through generation and shrinking, we'll think about how do we know that our generation, that our testing has been effective. And in lucid property-based testing, which is currently under submission to WIST 2024, we talk about this paradigm of lucid property-based testing that helps to cover the case where programmers are missing important bugs because their PBT is not set up correctly. There were examples of this in our study where developers shipped bugs into production because their testing wasn't set up the way they thought it was. And we present a tool called Tyche, which provides a novel ensemble of visualizations that shows developers what happened during their testing, so that they can evaluate whether they're happy with that. And this paper includes user studies for design and evaluation of these tools. So we're really kind of bringing together the kind of core property-based testing stuff with some real user-centered research. I'll talk about the design exploration first, then some principles of what lucid property-based testing is, then the tool Tyche's design, and finally the evaluation we did. For the design exploration, we had 5 participants who were experienced users or maintainers of a property-based testing framework called Hypothesis. The idea was to kind of iterate on a tool's design with the help of experts, so that we were keeping real use cases in mind throughout the process. This design iteration led us to 5 principles for what a system like this should be doing to help developers evaluate their testing. And here's the 5. The first is visual feedback. State-of-the-art tools usually print things to the terminal, and sometimes it's like complicated statistics being dumped to the terminal, and it's difficult to interpret. We thought that visual feedback was a really important way to help developers understand what's actually going on at a glance. Workflow integration was really important to the participants in our study. They don't want to have to change fundamentally the way they do testing. They want this to be integrated into their development environments, their code editors, or however they do their work. Customizability was key. This is because every property-based testing situation is different, and developers need to be able to tell the system what's interesting about their particular domain. There's no one-size-fits-all solution for this. Details on demand is this idea that we should present the developers with a kind of high-level overview of the data that they have, but then allow them to drill in to really inspect deeper specifics. There's good evidence that fostering curiosity during the debugging process makes developers better at debugging. And so giving developers tools to kind of dig into things and understand why things are happening is potentially really important. And finally, standardization. We want a single way for developers to be able to evaluate their PBT across frameworks and language ecosystems. This means that we don't have to develop this tool a whole bunch of times in Python and Haskell and OCaml and whatever. This can be done kind of once and used a bunch of times. So what does Tyche look like? Basically, it's an interface which sits next to the developer's editor and helps them to understand what's going on. When their tests run, this is step 1, it collects a bunch of data about how those properties are running, what inputs were used, etc. Then the view renders with charts and graphs and examples that the developer can take a look at. They explore these by clicking around through the interface, drilling down into different data bars. And if they find something they don't like, if they find that their testing isn't covering things that they think it should be covering, then they can make some changes and go back into the loop and try again with a better testing setup. We evaluated this technique through a kind of self-guided online study. We had 40 participants recruited from Penn undergrad and master's students, as well as social media. And the idea was to determine if our interface, if Tyche, helps developers to evaluate different property-based testing generators. The setup looks something like this. We started out with some kind of background on property-based testing and some instructions. We then had a few sense check questions just to make sure that participants were paying attention. And then the bulk of the study were these 4 tasks. In each task, developers were shown 3 generators, or the outputs of 3 generators, and asked to rank them in terms of their perceived bug finding power. In one case, developers got Tyche, the full interface with all of the data that Tyche provides them. In the other case, developers got a kind of control interface where it was like Tyche, but with a lot of the interesting cool features stripped out. And the goal was to see if the developers who saw Tyche instead of the control made fewer mistakes in ranking the generators. And we found that indeed they did. In 3 of the 4 tasks, there was a statistically significant effect showing that developers made fewer mistakes ranking the generators when using Tyche versus when using the control. In the last case, we found that it was likely too easy. Developers were kind of making very few mistakes across the board. And so there's more discussion in the dissertation as to why that happened. The upshot of this section is that lucid property-based testing, this new paradigm, helps developers to evaluate the quality of their test suites and ensure that their testing is effective. So that is the kind of body of the dissertation. I have kind of three main areas of work: understanding PBT use, advancing testing tools, and improving PBT analysis. What I want to talk about in the few minutes I have left is future work. What's next for me and what's next for property-based testing research in general. So allow me to kind of paint you a picture of the future of property-based testing. I'm going to do this in the context of an integrated development environment. We're imagining a world where the developer has property-based testing tools in their editor that's helping them throughout the process with different parts of the PBT workflow. And so let's start with the first part. So when writing a specification, the kind of first part of property-based testing is, how do I write a specification? Developers need help, right? This is shown in our Jane Street study, as well as the study we did before that. Developers don't always know how to write the properties that they have for their code. And this is going to be one opportunity to pull in a thing which is quite in the zeitgeist of computer science right now, but which I have not mentioned up to this point, which is large language models, right? I think that generally speaking, having large language models simply write tests for you might not be the best idea, because testing is kind of the trusted computing base of your application. It's kind of the core that defines what correctness means. So you don't want an LLM going in there and just writing tests for you. But I think there's a huge opportunity in using things like large language models to identify the kinds of properties that might be useful in a code base, and then to use more classical methods to help the developer build out those properties in a way that is easy and effective. That's the specification process. What about generation? Well, I think that we need to keep pushing on automation really hard. I have ideas in the direction of kind of using program synthesis techniques to aid in building generators for developers. And I hope that in the next few years, we can get to a point where, for kind of average use cases where developers are, their code is unique, but it's not terribly complicated, that they can just get generators that work well for their application for free, kind of derived from information that is already in their application, rather than having to kind of go out of their way to write data generators. And then finally, on the analysis side, I think we need to continue working to understand what it means for a test to be effective. The gold standard kind of is and has always been code coverage. How well do the tests cover the code? But there's lots of evidence that this is a kind of necessary but not sufficient measurement of code correctness. And so I want to keep pushing. I did some work early before my dissertation work on combinatorial coverage. And I think that between combinatorial coverage and other novel ideas of kind of testing effectiveness metrics, we can do better at coming up with ways of qualifying the effectiveness of a test suite. And together, I hope that all of this kind of comes together into a development environment that helps users get started with property-based testing and keep using it, so that property-based testing can become a thing that the average developer is using on a day-to-day basis to make software safer and more effective. And that's all for me. I also have some stuff up here that has nothing to do with my dissertation, if you're curious about the other stuff I have going on. And thank you all for listening.
Okay, thank you, Harry. We're going to transition now to questions. So we'll start with Hila. Can you make sure you can hear and that you know she's going next?
Hila, did you hear that?
I heard my name and I heard we'll start with, and I didn't hear the rest of the
Your
sentence.
question. You can ask questions first. You get the first shot at the questions.
Yay. Okay. In that case, I have two.
Cool.
The first is with regards to the user study for the WIST submission.
Yep.
I was wondering what was the logic of including novices in PBT in this evaluation. Like what do they contribute? What knowledge do they contribute? Especially since they're about half the population, right?
Yeah, there's more statistics in the dissertation on the kind of breakdown of I forget off the top of my head, but something like half, yeah. So let's see. I think my hope with Taiki is that it's not just a tool for experts. I guess it's not like aimed at expert users in particular. And we also had ideas that maybe Taiki was actually kind of specifically useful for things like education, where people don't understand what's going on during PBT, and then they see this extra information and, oh, now I kind of understand what's going on. So I guess we didn't feel like ruling out novices was necessary, because they're kind of in our target population of would-be users. I guess that's my answer. Do you have something more specific there that?
So I was wondering what you actually learned from them, considering like these are people I'm assuming that learned what PBT is from your intro in the study, right?
Yeah.
Like what did you learn back from them?
So we did have a kind of, in terms of the data, when we tried to kind of break it down to see like, were the trends different for the novices? Mostly no. When it comes to the like free form, we had some like free form questions at the end that they could submit. We haven't done a deep analysis of those to see if like there are things from the novices that are particularly important. But yeah, we didn't see trends in the data for the novices that like went against the broader trends or anything like that.
Is this surprising?
I don't think so. Like I think that let me think. I don't really think so. I think that like Taiki was designed to be a tool that kind of provides strictly more information than the current tools provide, and that information is kind of equally useful to someone who really knows what's going on versus someone who is seeing this information new. Like the information is kind of new to both groups in a way, at least in the form that it exists. I'll think more about that though, especially if the WIST reviewers have similar questions and we need to, the rebuttals are in a couple of weeks. So
yeah. And then my second question, I guess, is an easier question because it's a little more philosophical, which is, in your grand vision for the future, you're basically talking about branching out to what is essentially like all the programming languages, which I guess asks or begs the question of how generalizable your approach would be outside of, I mean, I know you did some work for hypothesis, but most of the work for PBT has been in the functional or semi-functional realm.
I think that property-based testing is really useful in imperative languages as well. And I think the reason it's going to be it's useful in those areas as well is because everyone who's writing clean, well-abstracted code wants a complicated, well-abstracted thing at the core of their application, right? And so testing that with property-based testing, whether it's in a functional language, whether it's an object or a function, doesn't super matter. Now, the purity that functional programs often lean towards is a thing that has made PBT extra useful in the functional space, right? It's a thing that it's the reason PBT has existed in the functional space for so long. But there's even ways around that. There's, you know, techniques and hypothesis, and you know, I've done some. Where's Ernest? Is Ernest here? Oh, hi, Ernest. Yes. Ernest is in the room. We've worked on sort of testing code that, including imperative code in OCaml. So yeah, broadly, I think property-based testing will probably need to adapt a little bit as you sort of pull it into more imperative languages. But I think property-based testing has a kind of targeted use case across lots of different languages and paradigms.
Thank you.
Thank you. Meyer next.
Thank you very much, Harry. This was an excellent talk. I have 3 questions, and I'll be quick in the interest of time. So the first one is, you know, can you comment a bit on what kinds of bugs did you find, you know, especially given the sort of the real-time requirement that people run property-based testing, you know, while development?
Sorry, I was fixing the Zoom and I blanked. Can you just repeat the question again?
Yes, I'm curious to know what kinds of bugs property-based testing found in your user study. There was just one comment there which said, where some developer said it can find things that, you know, we didn't think of. I'm just curious to know more.
I don't know in that particular case what that developer was talking about. I don't think we got the specific bug that they were referring to. Although I think that a lot of the time when it comes to sort of the cases they weren't thinking of, these are cases that fall outside of what the developer was necessarily considering as their input space. It is in the input space. It's a valid input to the application, but it's just one that sort of is a little unusual in a way that you know, things like strings with Unicode, where strings with like weird Unicode characters, where like you wrote your code assuming you've got ASCII, and then there's these weird Unicode characters, which, you know, it's valid for your application to take, but you sort of just didn't even think that you hadn't thought of that part of the input space. I don't have the nature of the PBT in practice study was that, like, because these were interviews, we did lose a little fidelity in terms of like specifics of code examples and things like that. There is currently a study going on, I think at Northeastern, that is attempting to kind of catalog a bunch of properties in the wild and hopefully also kind of keep track of bugs that those properties have found. So we may have more information on that when that study is done. Yeah, I hope that's a good enough answer.
Yeah, and I suppose some developers might want to strengthen the precondition, right, in response to certain.
Yes, they might have found that, oh, actually, we should really only be taking ASCII characters. But in that case, like, in some folks worry a lot about this, where they're like, well, but what if the developer finds a problem in the spec? I was like, well, that's a bug too, right? So like, I don't know, I don't have a philosophical qualm with the idea that property-based testing is there both to help developers fix their code and to help them fix their specs. I think that's perfectly reasonable.
Great. My next question is, you know, about shrinking in reflective generators. You seem to have described a core component of it, right, which is sort of this backward generator. Can you comment a bit about the bigger picture? For example, you know, how does it relate to delta debugging? Is there an oracle function when this process realizes that it's done? And is there any guarantee? Is it like one minimal or something like that? Or is it just heuristic?
So the reason I didn't focus on this too much is because the actual algorithm we use to shrink the choices is from a different paper. We didn't design that. We only designed the part where you sort of run the generator backward. It's a paper by Dave McIver from 2020. I can find it for you, but their algorithm guarantees that the choice sequence you get is short lex optimal. So it's the shortest and lexicographically smallest sequence of choices that still produces something that triggers the bug. I'm like I think that optimality is nice. I think in practice, anything that helps to get the developer from big, intimidating input to input that I can fit in my head is like good enough in my mind. But those are the guarantees that the algorithm we use give.
Sounds good. And my last question is, I'm curious if you ran, your tool long enough, like let's say in AFL mode, right? Beyond sort of, interactive developer mode, and just observed it, right? What did it find? Clearly, it must be generating valid inputs, but how interesting did the inputs get?
Yes. So Hill and I have been talking about this for a while, and I'm just waiting for the right student to help, because I feel like it's a great project for a student. But I would love to run PBT for a long time and see if you run it for as long as people run the fuzzers, like, does it find the same bugs without doing the coverage stuff? I think like it's going to depend a lot on the different use cases. And so there's an art to picking the right examples to like get a good sense of what's going on. But I do think it's an interesting question. And I do want to keep focusing on property-based testing for the kind of short run unit testing thing, because I think that like that's the use case where I, as a developer, would use it the most, and where the developers we spoke with would use it the most. But yeah, I definitely want to know, like, in the limit, at what point do you switch over to the fuzzer, right? At what point is the fuzzer better versus like, how long should I just run this standard generator for?
Great, thank you very much. I see lots of opportunities for future work here using, say, LLMs, program synthesis, and also at the intersection of security and software engineering and HCI. Yeah, so great job overall.
Thank you.
Okay, so next we'll go to Andrew over here. And perhaps you can repeat Andrew's questions.
I'll repeat Andrew's question for the Zoom. Yeah.
Thank you, Harry, for the talk. So, as part of the Titan project, you have this core usability study that shows usability of these use of input distributions. You also have these other cool tools around the free generators and the reflective generators. I would be easier to take, the same approach to usability study design and try to apply that to some of your programming languages where, for instance, take the example of the free generators and trying to ask about the quality of the types of things that those free generators do. What's a study that you could design to try to get to the bottom of that question?
Yeah, okay, so the question is, how could we maybe design HCI style studies to examine the usability of the PL contributions, not just the HCI contributions? So I'll give a non-answer and then I'll answer your question. But my non-answer is that I consider both free and reflective generators to be more theoretical contributions than kind of tools that I think a developer can really pick up and use. And so I expect if we kind of put developers in a room and said, use the reflective generator, they would have a hard time because it's not designed that way. But to answer your question about how to design it that way, maybe. I think the answer is to keep pushing on the theory and to keep pushing that theory towards the practice to the point where we have something which does cover a kind of large enough space that we think someone could pick it up and use it. And then I think I'm particularly interested in getting hypothesis users who are maybe doing something a little bit more advanced than other hypothesis users, or maybe just your average hypothesis user, and saying like, okay, suppose in your application, their real world application, you wanted to improve your shrinker. Here's a little documentation on kind of how these reflective generators work. Do your best to kind of improve to turn your generator into a reflective one, and just see how, where the pain points are in that process. I think, I know of some of the pain points with kind of usability around reflective generators, but they might not be the ones that developers actually run into. So before we, really polish that, I think that would be the goal, is to kind of examine with a developer in the room on a real code base, how easy or hard it is for them to apply these kind of new generation abstractions.
Yeah, I think that's a really good idea. And another interesting angle to think about, that I'm curious of your thoughts on it. You have this cool graph with regards to the free generators about producing these more kind of fully formed input distributions. I'd also be curious how you would take, what kind of approach you would take to try to identify, are those distributions interesting? Are those distributions like improvements from the perspective of like, what a tester would want to see?
Yeah, I mean, I think doing that, the thing that makes most sense to me would be doing that in the context of Tyche, right? Is sort of applying Tyche to the distributions produced by the free generators, and going from there, right? Like showing the developer, hey, here's what Tyche looks like when run on the original generator versus the choice gradient sampling algorithm. And I think we may learn multiple things at once. We may learn gaps that Tyche still has, but we may also learn things about, whether that distribution has improved in that developer's estimation. So I think Tyche is maybe a great tool for experimentation in that sense, because once we can get it to a point where we can sort of control for its effect in the process, it gives us a nice platform to evaluate developer understanding of distributions.
So another question, going back to the reflective work, I was wondering if there are limits on the kinds of data structures that you can back parse into choice sequences and kind of use reflectives on.
No. Well, okay. So like practically no, with two big asterisks. The first is that from a computability perspective, to reverse a generator of well-typed terms in system F sub, or a similarly complex programming language, because type checking is undecidable, because type inference is undecidable, you actually can't decidably go in reverse. This is way more complicated than anyone really wants to get into right now, I'm imagining. But the point is that there are cases where the reverse direction may never terminate if you've got a really, really complicated input. That's in the kind of periphery of use cases. I think, and like when we've applied this in practice, like all of the even very complicated generators that we have, when we tried to turn them into reflective generators, it works, you get a reflective generator. The other big asterisk is that it's not always very easy to do, right? You sometimes need to have some kind of interesting insights on exactly how to write the reflective generator, how to change the generator to make it reflective. It's not like it's not always a mechanical change. Sometimes it is quite mechanical, but sometimes there's insights needed. Does that kind of make sense?
Yeah, that makes sense. I wonder, maybe there's no way to say this without stating it more formally, but like, is there like a general universe of types of things that are like well within the realm of reflectives? So you mentioned like binary search trees as one example. DFAs,
Sure.
Generally,
DFA's graphs, like, I think no harder than standard monadic generation of these things, which is not trivial. Like writing a monadic generator for graphs is not that hard, but it's also like a little non-trivial. And so like the reflective generator is also a little non-trivial. I think like my general take is that like most data structures that programmers are using in your average program could in principle have a reflective generator for them. I think some are complicated enough that it's not worth the work and effort, at least not always. I think when you get into things with really complicated types like gadgets and things like that, you might run like, I don't have a clean characterization, but the thing that people guess with reflective generators is, oh, you can't do things where there's like, okay, I'm not gonna keep, I'm rambling now. You can do it with a lot of stuff, but there are things where it's pretty complicated.
All right, one last question, and you can invite your future work. One of the directions that you're considering is giving people assistance with specifications. And one of the things that I wondered is the extent to which you could rely on the prior, like, either formal specifications or like pseudo specifications that people have written within their environment in order to see the types of specifications that you would kind of synthesize in actual code, which ended up leading me to think of, do you, from any of the types of interactions that you've had with people who write these specifications, do you have a sense of the frequency with which there are existing specifications written around that imply the intended behavior of code at the time that someone would actually want to write down an actual coded specification, something like hypothesis or check?
So I guess the question is, do I have a sense of how often there's kind of already an informal specification, maybe written somewhere in the code at the point where someone wants to write a property and formalize it?
Informal or formal, like if you want to write something like TL layer, like a higher level modeling language or writing.
Sure. I don't have a sense. I think it's going to be really domain dependent. There are areas, companies, organizations where there's process around this, and then there's areas where there's no process, and then when there's no process, who knows what's going on. And so I think I would be shocked if it's usually the case that there's a specification at the point where someone would want to do PBT. But I wouldn't be shocked if, I'd be shocked if it was 80%. I wouldn't be shocked if it was 30%. I think there's often going to be opportunities to build on specifications that already exist in one form or another.
Great, thank you. That's it for my question.
Okay, so I'll be brief, that the other committee members asked a lot of the questions that I just wanted to ask, but I'm gonna actually pick up one of those questions and go a little bit deeper and maybe take it in a different direction. So she was asking sort of about the relationship between the work you've done at Haskell and the work you've done in Python, the user studies you've done in Python. Your dissertation doesn't say this explicitly, but it doesn't not say it, that there's a difference between the two, right? It kind of just assumes that PBT is PBT, it doesn't matter which language you're in.
Yeah.
I want you to comment on that.
Sure.
And
So-
I'm specifically asking about the language.
Okay, so
Not the difference between functional and imperative
Sure.
programming, the actual
Sure.
features of the language.
Sure. Okay. So the question is how is PBT different in different languages, and why does my dissertation pretend that it's not? So I think the big difference between the way property-based testing works in Python and versus Haskell is really that Python refuses to kind of be constrained by, we're not going to change state during generation, and we're not like in Haskell, generators are pure with the exception of the randomness. And so you have a really constrained system in which, you know, a generator is one thing, and you can sort of design things around all generators, and it just works and it's clean. In Python, people need to be able to say, what if I need to access a database during generation? The other thing that comes up in Python that's a difference is class-based or kind of testing of a class as a thing, which there's tools for in Hypothesis that don't exist in exactly the same form in Haskell. So let me so these are the two differences, and let me sort of comment on each. So the first, when it comes to the kind of generators and the effects during generation, my hunch is that people usually don't access the database during generation, right? The Hypothesis developers are very, very defensive that they be able to, but like if they don't, we can do all the same things we do in Haskell. And so I'm making a little bit of a gamble in a way that I think that a lot of the theory that we do in Haskell can transfer into Python for the average case, for the common case. And that when it's an uncommon case, the developer probably knows what they're doing, or at least we can maybe give developers ways of kind of getting out of the system that we've put them in. So I sort of want to operate in this world where we can still target the common case of the Python generators, because it gives us such power to do things cleanly for that kind of subset of the space. And then when it comes to the kind of stateful generation thing, I mostly think that is an unfolding of the same problem that we get in like classes are their own way of organizing data, but I think the class-based testing that is done in Python is really not that different from similarly structured things that we do in Haskell and OCaml. So I think for that, it's more of a superficial difference than people really tend to think. For example, the work that I've been doing with Ernest uses similar ideas to the class-based generation stuff, but in OCaml to work with modules. And so like, yes, every language's abstractions are going to slightly change the way you need to think about how property-based testing is organized. But in the majority of cases, I think the theory is still going to kind of take the same form, and it's just kind of how you bend it to fit one abstraction or another. Is that too hand wavy? Like, is there something more specific I can? Yeah.
So the follow-up is in your IDE for property-based testing,
Yeah.
you talked about standardization.
Yes.
And I want to know, should I imagine that standardization as the intersection of what you can do in all of these languages, or somehow the union? Like, this is a tool. Can you use this tool to bring new capabilities over to libraries for PBT across languages? Or are we going to be restricted to what you could do in every single language?
Okay, so the Tyche as it currently exists is absolutely the intersection, right? It is a common set of things that work in quick check and Hypothesis and whatever. And like, there's a little bit of flexibility in that. So like Hypothesis has code coverage information, which quick check can't provide easily. And so, you know, we allow Hypothesis to provide that, and we allow quick check to omit it. But we have really in the standard, we have kind of intersected what we thought are the kind of reasonable things and left out some stuff that we could have done in Hypothesis were we not so concerned about standardization. But what I want to argue is that at least in the case of evaluation, I really do think that there's more similarities than differences. We're dealing with a kind of analysis of an output of a program, which doesn't need to be concerned so much with the structure of the program that produced that output. And so lots of different, if you look at the examples we have for like code that produces Tyche output, we've got a stateful class-based test in Python and, a super functional BST implementation in Haskell. And both are outputting the same data format, and neither is straining too much to make that make sense. And so I think that, like, in the case of evaluation, I think we really do have a lot of leeway to standardize without hurting things too much. When we start adding IDE features that are a little bit more language specific, or that get into specification and generation, I do worry that we'll need to drop standardization a little bit. That like we may need to say, okay, here's the version of the PBT IDE you use in Haskell, and here's the one you use in Python, and those are going to have different features. But they can at least be, I think, inspired by the same principles and ideas.
Okay, I think I should stop here. Maybe if there's a quick question, we have time for one quick question from the audience. Oh,
Thank you, that's great talk. As you know, one of my PBT real world use bugbears is the bootstrapping problem. Wherein sometimes it's hard to get an organization that doesn't already do PBT to a point. So I'm curious if you would speculate with ways that this sort of new lucid property-based testing paradigm could maybe help the bootstrapping problem, help people convince their colleagues and how to.
Yeah, so the charts that we produce in Tyche appear in your editor right now, but there's no reason they can't appear in things like reports or other artifacts that developers can produce to share with their teams. So this is one thing that I think is like a really great opportunity for the Lucid PBT framework, is to be able to automatically generate things like reports and documentation. I was hoping to be able to do that with some DARPA folks, although it seems like software certification is really a whole thing. But in general, I think that yes, I think lucid property-based testing can produce evidence that PBT did a thing, and that evidence can be brought around to lots of different stakeholders to help to bootstrap PBT in an organization.
Who should not use PBT?
Who should not use PBT? I think all developers should have property-based testing in their toolbox. I think some will use it much less frequently than others. I think developers, you see, I'm tempted to say folks like game programmers who exist in a kind of world where everything is so interconnected that it's really impossible to kind of isolate a clean abstraction that you could test on its own. But like, I should ask the folks who do games programming that I work with about that, because like maybe I'm just wrong and there are things like I really think like programming is fundamentally about abstraction, and where there are abstractions you can do some property-based testing. So I think like it should be in everyone's toolbox and then applied where it matters, where the code is supposed to be correct. It's really important that the code is correct, and where it's not so hard to bend your code into a place where property-based testing can be applied.
Let's thank you.